Okay, so welcome to lecture 8. And in this lecture, we're going to start writing our own proofs. Now, in the previous lectures, outside of the Python stuff, we've learned a lot about logic, right? We've learned about conditional statements, propositions, quantifiers on compound propositions. And this is all leading up to today's lecture and then the next lecture. And by that, I mean, we're going to use the rules of logic to argue why mathematical statements are either true or false. Okay, and this is what a mathematician does, by the way. If you've ever wondered what a mathematician does, it's precisely prove and disprove statements. We don't sit around like calculating a bunch of things or numbers or whatever. We are typically thinking in a logic-based system of trying to figure out the truth value of some statement. So we're going to start very small. We're going to start our proof arguments with simple statements about maybe even and odd numbers. So with that in mind, I need to write down these definitions of what it means to be even and odd in a formal manner. So definition. I'm going to say let n be an integer. Okay, so again, this is notation I've used before. It just means that n is an element of the integers. And integers are positive and negative whole numbers. Okay, so n is just one of these positive or negative whole numbers. N is even if, let's say, I'll write it using quantifiers. There exists an integer k such that n is equal to 2 times k. That is the formal definition using quantifiers and the logic symbols that we know of being even. Okay. Now again, we have to remind ourselves of what this quantifier is saying, right? So it's a definition, right? So we're given some value n, some integer n, right? And we want to like consider the case like if it's even, right? If this is true, then it's even, which means that we have to consider this existential quantifier. There exists k in the integers such that n is equal to 2 times k. All it's saying is that if you can find some integer k, like for example, like maybe I'll just put an example right here. What if n is equal to like 6, right? In order to show that that's even, we have to show that there's at least one integer so that that n is equal to 2 times that integer. So here, k would be what? 3, right? Because this is equal to 2 times 3. Okay, so showing the existence of such an integer proves that it's even. If there is no such an integer that satisfies that, then it's not even. Okay. Now, in a similar manner, we say that n is odd if there exists some integer k such that n is equal to 2 times k plus 1. So that's the formal definition of being odd. Okay. So as an example, if n is equal to 9, k would be what? 4, right? So in this case, k would be 4 because 9 is equal to 2 times 4 plus 1. Okay. I wonder if my mic picked that up. My ankle just popped. Yeah, that was really loud. It didn't hurt or anything. It's just my tendons are getting used to moving. That was funny to me. So do we understand what it means to be even and what it means to be odd now? In a formal sense, right? A lot of people, a lot of students that I've encountered in the past immediately revert back to, like, is it divisible by 2 or something, right? We're ignoring that business, right? That is the definition. In order to show something is even, we have to find that. There's no divisibility that we're going to consider. So now that we have these definitions, I can pose to you what I'm going to call a conjecture. A conjecture is a mathematical statement that we do not know the truth value of. So let's consider a conjecture. So if n is even, then n squared is even. Okay. Now, this conjecture is, there's a quantifier here, right? There's a propositional function as well, right? If I were to translate this to symbols using the logic that we know, it would look something like this. Like this is equivalent to saying like, for all n that are integers, if n is even, then n squared is even. Right? These are like the same statements. In order for this conjecture to be true, this universal quantifier applied to this conditional must be true. So the universal quantifier, in order for the propositional function that follows it, if this statement is going to be true, it has to be true for every single possible n. Right? Now, okay, every possible n, there's even n and odd n, right? So what if n is odd? So for any odd n, is this conditional statement true or false? It's true. It's true because if n is odd, then this is false. False implies anything is false. Remember that I was trying to emphasize that if you have a conditional statement and the hypothesis is false, then the whole statement is false, right? So if n is odd, we don't even need to care about it, right? But if n is even, then we have to be careful because that's satisfied. So if this part is satisfied to be true, we need to verify that this is also true. If this is false one time when that's true, then the whole conjecture is false. And that would be called a counterexample to this conjecture. Okay. So the way that I'm going to set up the proofs for you is in 2 parts. And I was actually taught this by Dr. Delavigna when I was a student at UHD in discrete math. There is a formal part here. So if you see PUF, it's abbreviation for proof. Whatever you write after this better be formal and nice looking. Over here, I'm going to put my scratch word. Okay. Now, this is where we're going to figure out the steps of the proof if it's true. And then also, if we're trying to like figure out those steps, we might find a case where it's false. Right now, we don't know, right? But what is your intuition by looking at this conjecture? Like, do you think it's true or do you think it's false? You think it's true. Why do you think it's true?
Because if you put 4, the first phase is 10.
So if you put 4, then the square of it's 16, right? So this would be an example where it's true, but it doesn't say to me why it's always true. So you're like trying to piece it together, right? And it's my job to help you understand how to do this. Now,
If you multiply two even numbers, your result is even.
but why? Well, we're about to figure it out, actually. Let's figure it out, and then I'll come back to what you'll get it. Let's do some scratch work first. So the way that we're going to approach trying to prove this conjecture or trying to figure it out is in a direct way. So, well, I think you're close to what I'm probably going to write down, like right here. So a direct proof, and we don't know if it's true yet, but we're going to try to prove it directly because our intuition tells us that the statement's true, which can be deceiving sometimes. Direct proof, assume the hypothesis to be true. This is the simplest form of trying to prove a conditional statement. You assume the hypothesis to be true, and you try to use that information after that assumption to imply something about the conclusion. So anytime you're doing a direct proof, you do not have to let the reader know what type of proof that you're doing. There's a few other techniques that we're going to learn where you're going to have to tell the reader. Direct proof, we don't have to do that. We just assume the hypothesis. So in my scratch work, I'll say something like n is even. I'm assuming that to be true. Okay, so n is just some arbitrary integer, and I'm assuming it to be true. It is even. The hypothesis is true. If it's even, what do I know about it? You almost said divisible.
There's just the k, there's just the k, multiplied by 2 that equals n.
Right. So this right here, n being even, implies that n is equal to 2 times k for some k. Right? If it's even, that means that this is a tautology, right? Which means there has to exist some k. That n has this form, right? We don't know what that k is because we don't know what n is. We just know that n is even, right? So this follows by definition, right? We didn't write it in our scratch work, but if we assume that, we get to this next line by that definition, okay? So now that we've made an assumption, we've applied a definition, we have something to work with. Now we need to look at the conclusion and like think about what we're trying to do. We're trying to show that the square of that thing is even, right? So let's go ahead and square that and see what happens. Maybe we can make it look even, right? So if n is equal to 2k, and that means that what? N squared is equal to, exactly. And if we look at 2k squared, that's equal to 4k squared, right? 2k times 2k is 4k squared. Now, is that even? The answer is yes, but it doesn't look even to me. It does not look like that. Where is my integer 2 times some integer, right? I don't see a 2 there, right? The definition has a 2. Yes. Almost. What we can, exactly, we can factor a 2 out of that 4. Isn't that the same thing? Now I see 2 times that. Now, I'm just going to go ahead and tell you that the integers are closed with respect to multiplication and addition. And by closed, I mean, if you multiply 2 integers together, you get another integer. If you add or subtract, you get another integer. And so the integers are closed under these operations, which means that 2k squared in parentheses over there is an integer, which means we have found the existence of an integer that makes n squared equal to 2 times that integer. So I can even write that like 2k squared is an integer means that n squared is even by the definition of being even. If I can write u, in this case n squared, as 2 times an integer, that's it. I showed the existence of this in this definition.
So basically, the 2k squared becomes an k.
Yeah, yeah. And don't get too hung up on the k. You can use whatever variable you want, right? Like I could just, if I wanted to be like very specific, I could like say this thing was equal to a or something, and then it's 2 times a, and a is an integer, whatever, right? So this is my scratch work. I think it's true. I can tell from my scratch work that this conjecture is true, and now I need to formalize it. Now, it's been my experience in the past that CS majors in particular have a they're very hesitant about what I'm about to do. Let me write out the formal proof and then we'll talk about it. Okay, and I'll mention these hesitancies I've experienced in the past. Okay, I'm going to start the proof by elaborating more on that first bullet point. And by that I mean, I'm going to say, let n be an even integer. We're writing out a story right now, and we want the reader to read each line without having to like second guess themselves or pause, right? So is that first sentence clear? Okay, if you didn't know what even was, you could look up that definition and you're good. If you didn't know what an integer was, you could look up the definition of an integer. Okay, it's descriptive enough to get us started. Now, I look to my scratch work and I see, what did we do next? We wrote n is equal to 2k because of the definition of being even. So I'm going to tell the reader that, right? So by definition, n is equal to 2 times k for some. Now there's 2 ways I could do this. I could say for some integer k, or I could write for some k that is an integer. Which do you prefer? It doesn't, now I just happen to write that right now, but which do you prefer? Writing this or saying for some integer k? Like integer k versus the symbols. It really depends on the audience that's going to be reading it, right? Like even all of you are probably still hesitant about this notation right now. I've used it a bunch, but still the hesitancy is there. And if you're writing a proof to share with your peers, right, you might want to be more clear. So I'm going to go ahead and get rid of that and write it out. Another reason why I'm deciding to do that is in the first sentence, I don't use that notation to indicate n as an integer. And I want to be consistent, right? I want to use the same style here as here. And if you think about coding, you should always do that. You should always have the same style per code block or line. Same idea. So for some integer, All right. Now, I think that we can all understand this better a little bit now that I've gotten rid of that symbol. Okay, so what did we do next? We applied some algebra, right? So we can do that. So then n squared is equal to 2 times k all squared. That's clear because n is equal to 2k, so n squared is equal to that squared, right? And then with some algebra, this becomes 4k squared. And then if we factor out a 2, we get 2 times 2k squared. Okay. Right, so we're almost done, right? We completed the algebra part, and then now we need this last bit of the scratch work. There's like a conditional sign. It looks kind of messy. We need to fix this. So maybe we could say something like, oh, put a comma there. Emphasize the break before the equation starts. Okay. Maybe we could say something like, since 2k squared is an integer, n squared is even by definition. Referencing back to the definition, so if they forgot what the definition was by that point, they can go back and look it up. So this chair is not rolly, so this is going to be hard for me to write and fit, but maybe like, since 2k squared is an integer, n squared is even by definition. Are we done? What just happened with all of this? We assumed that to be true, used the definition in equivalences of equations, and showed that that must also be true. That quantifier applied to this statement, it's always true. That's a tautology. The conjecture is true. We've proven it. And we put our stamp right here, put a little box to say that we're done. No longer conjecture. This would be a true statement now, so we have two options to call it. We can call it a theorem or a proposition. These are a mathematical proposition, not a logical proposition. There's a relation, but it's kind of a difference. A theorem is something major, something that took like a lot of work to do. This I would call a proposition. We proved it relatively easily by just applying the definition in some algebra. So I call this now a proposition. N is even, and n squared is also even. Okay. Now this little box right here is indicating to the reader that we're done. It's a box that represents QED, which is an abbreviation of a Latin phrase, quod erat demonstratum. It roughly translates to what was to be demonstrated. Start, argument, what was to be demonstrated, done. I actually have that tattooed on my arm right there. I got that when I finished my PhD. So look at that carefully. Notice I was trying to squeeze it in. It's straight right there. Straight right there. Periods. commas clearly explained with words. The purpose of proofs, the best proofs are the proofs that are the simplest and the most understandable. There's nothing extra in here that we don't need. It's exactly what we need to argue why this is true. Okay. And again, just to reemphasize, if n is odd and this is false, it's true because of the definition of the conditional. So if we consider the case when it's even, then we deduce that the conclusion must also be true. It's always true. We're done. This is true forever, for all of time, right? And this is actually a good point to emphasize the differences between a science and mathematics. Mathematics is not a science. Mathematics is a philosophy. Nothing in science is completely true. Yes, science can make measurements that are absurdly precise. But logically speaking, those measurements, there's round off error, there's things that are influencing the measurements. That's different than this. This statement, if n is even, then n squared is even, is true for all of time, regardless of what you try to tell me. We've just proven it to be true. Moreover, do we understand why the square of an even number is even now? Back to what I was kind of poking at you with before I wrote down the argument. It's even because, like, could we describe it to someone else with our words? Like, why is the square of an even number even? Tell me. You're like right on, you're like close, but I might simplify it a little bit more. So you were saying like, because 2k squared, you're gonna kind of word it out like that, right?
Sure.
What about the square of a number is even because if the original number is even, then it has a factor of 2. And when you multiply that number with each other, there's still going to be a factor of 2. There's still a factor of 2 because the original number had a factor of 2. Does that make sense? So now the detail that I require you guys to do when you're writing these proofs has in the past annoyed CS majors and discrete math because it doesn't seem immediately applicable to programming. However, think about what's going on here. It's a line by line argument flowing from top to bottom. And the clearer it is, the easier it is for someone else to understand it. Imagine you're writing code. What do you want? Top down? You want consistency? Simple?
Cool.
You don't want anything extra in your code that's going to confuse the person reading your code. Like, why is that there? And then they start thinking about it, like maybe they missed something. And it almost, in a sense, is algorithmic to do this. In fact, it is algorithmic to write proofs. And writing proofs for statements actually falls into a class of problems that are NP-complete problems. They're basically like the hardest problems that you will ever encounter. Because you can put problems into classes, and the actual act of writing proofs falls into one of those hard classes. Okay. So it's been my experience in the past, the students that really try to nail down the proofs become better programmers. And when I look at their code, I'm like, yeah, this person knows what they're doing. It's not a necessity, but I think that it really helps. And it also helps you understand debugging as well. Understanding where there could be something false occurring. Right? Like division by 0, that would not be allowed in a proof. Right? So it is important. Now let's think about another one. So everyone understand these definitions? I can erase them. what about maybe we consider the odd version of this, right? What if n is odd? Is the square of it odd? Most likely. We should probably do a few examples to check, maybe. So like 1 is odd. Why is 1 odd, by the way? What's k for 1? 0, right? It's equal to 2 times 0 plus 1. That's fine with me. It's odd, right? So 1 squared is equal to 1. Okay, that's odd. Okay. What about 3 squared? That's equal to 9. Odd. All right. Things are looking up. It seems possible. What about 5 squared? 25? Okay. We have examples that make us think about a conjecture. Right? So let's go ahead and write that conjecture out. And again, when we're writing these mathematical statements, they really are conditional statements at this point. Okay? So we can say something like, if n is odd, comma, then the conclusion, right? Then n squared is odd. Okay. So how are we going to write our proof? What's the first thing we're going to do? Before that part. For all of you guys, when you're starting off writing proofs, and I even do this when I'm working on like my own research type of problems. Exactly. Give yourself some room. Don't try to just start writing this nice thing first. Like split it up and then try to figure it out first. We don't even know if that's true, right? We should kind of look at what argument might work, and if it does, we're good, but we still don't know if it's true, right? Because I didn't tell you that it's true. I just wrote conjecture. And if I ever give you a conjecture, do not assume that it's true, right? And I will. So we're going to use the only proof technique that we know, which is a direct proof, which means we need to assume that the hypothesis is satisfied and is true. The hypothesis is what? N is odd, right? So we're going to assume that N is odd. Now, what's the next bullet point going to be? What does that imply? We have to apply a definition. So typically, when you declare something to be true, you'll have a definition to work with. I declared that, so now I can use the fact that it's odd to write in a certain way.
There exists a number times 2 plus 1 equal to n.
Exactly. So n is equal to 2 times some integer plus 1. And I'm using my scratch work, so I'm just going to write that like for k in there. For some k, right? So we declare something, we look at it and apply the appropriate definition, we check back where we're going, where do we want to eventually land at? N squared looks a certain way. So let's go ahead and use this and square it and see what happens. Okay, so n squared is equal to 2 plus 1 all squared. So this is some algebra. We have what? This is equal to 4k squared plus 4k plus 1. Right? Now, is that odd? It is, but it doesn't look like it to me. What does it mean to be odd? It's twice an integer plus 1. That doesn't look like twice an integer plus 1. Can we make it look like that? What do we do?
Factor out the k.
Factor out the k.
2.
Yeah, there you go. So if I factor out a 2 from the first two terms in this sum, I get this. Close those parentheses, and then there's a plus 1 outside. Oh, now it looks like twice an integer plus 1. Okay, so we're kind of good. I would probably write another line just saying 2k squared plus 2k is an integer, and then we're done, but I'm running out of room. Okay, so this is our scratch work. Now we have to formalize it. So I'm going to make a declarative statement to get started. I'm going to say, let n be an odd integer. Good to go. And then I can do something. What am I going to say next? There you go. By definition, we know something about n. So by definition, n is equal to 2 times k plus 1 for some integer k. Ooh, I don't like it.
Professor,
Yeah.
if one carry 3 times 2,
6 and then plus 1 is 7.
yeah.
I am annoyed right now. This is like a very nitpicky thing, but I'm annoyed right now. What am I annoyed at? Whatever I did.
It's not written the same as the second sentence isn't written, I guess, isn't as consistent as the first one.
That's not the thing I noticed. I think that they're moderately okay right now, those sentences. But
Oh,
it's not lined up.
Oh.
It's not as professional as I would like it. Think about indenting your code when you're writing it. Stay consistent with your indentation.
I didn't even notice that. I didn't notice that.
So by definition, again, n is equal to 2 times k plus 1 for some integer k. Lined up better. So now we've used the definition. Our next step is to perform these algebraic steps. So we can transition to that with then. So then, comma, to indicate we're going to have like a little code block of equations. So n squared is equal to 2 times k plus 1 all squared, which is equal to 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k all plus 1. Okay, and now we're almost done. We just need to remind the reader of the definition.
The algebra is invented.
Yeah. Good in the middle. So then I can say since two k squared plus 2k is an integer, n squared is odd by definition. Period, and then QED. Okay. Now with these very, we're done, and it's no longer a conjecture, it's a proposition now. Proposition is a baby theorem. And since we've proven that to be a proposition, that statement is always true forever, for all of time, we know something about n when it's even, when it's odd and even now, and we square it, right? So what are we doing? We start with the definition, and then we use the notions of logic to deduce things and to prove statements. And the statements are quantifiers applied to conditionals in this case. And as we do this, what are we building? We're building like a theory, right? We have the definitions, and they just so happen to easily produce other things, and the things are these propositions. So, and it's nice, like if you think about it, you know now, you know for a fact that if you square an odd number, it's odd, right? No matter what odd number it is, you know that it's going to be odd. Moreover, the proofs in both cases here hint at an actual algorithm to compute the square. It's not like anything to like brag about, but there is an algorithm hiding in these proofs. In particular, I know, like, so let's look at like 9, for example. 9 is odd, right? What's the k for 9? 4, right? It's equal to 2 times 4 plus 1. It's like this right here, that's your k, right? So then the square of it is what? 2 times 16 plus 8 times 2 plus 1. You see like that k tells us something here? So breaking the number this way, we have a way of computing the square of it. It's not anything special, but if we know the k, there's a closed formula, it might tell us something about the square, right? Maybe, for example, we don't want to, like, I don't know, there could be a use case for it. And at least like in my own experience, I've written a proof before and then looked at it later and found like an actual decent algorithm in that proof, and then use that to like publish the paper. Okay. So these have all been examples of what are called direct proofs. There's another type of proof that we should probably talk about today. Okay. And I guess I'll start up here. I'm just going to erase this. The second type of proof relies on a very special logical identity that I tried to emphasize during lecture 1. And that is that if P, then Q is logically equivalent to not Q implies not P. Does anyone remember what I called this? Yeah, it's the contrapositive of the condition. So the statements we've been considering are conditional statements, right? So sometimes it won't be so easy to prove a conditional statement as it looks. For example, the following conjecture. If n squared is odd, then, actually, need more room over there. No, I'll erase that. Then, n is odd. This looks very similar to what we just proved, right? But it's not the same statement, right? The previous thing we proved, the hypothesis was what? N is odd. And the conclusion was n squared is odd. In this statement, the hypothesis is completely different. The hypothesis is now that n squared is odd implies that n is odd. You see that they're different statements, right? So if you were to try to prove this with like scratch work, right? So it's just like maybe try to prove this directly with scratch work and see what happens. So scratch work for this proof. So what would we assume? If in a direct proof, we would assume what to be true. Right. So we're going to assume like n squared is odd. And then we can apply the definition again. So that means that n squared is equal to 2 times k plus 1 for some integer k. And then we look back to where we want to go. We want to show that n is odd. Can we show that n is odd from that? Maybe you would try to take like the square root on both sides, but then you don't even know if you have an integer anymore, right? So we're kind of stuck. And if you try a direct proof and you don't see an obvious way, then maybe switch it up and try a proof by contrapositive. Because this is a conditional statement, if P, then Q, right? That is logically equivalent to not Q implies not P. So you have to be careful and identify your P and Q and then work out what the other statement is. So this right here, that's my P. And then this is my Q. So to prove this statement, we can say, what is not Q implies not P? Well, if you're not odd, you're even. Okay? If we just negate that, what do we get? So, oh no, we have to negate Q first, right? So what is this statement? So it is n is even implies what? That n squared, yeah, P is even. Or that the statement P is, you have to negate it to be n squared is even. Oh, we're done, right? Didn't we prove this to be true earlier? We don't have to write anything. Done. This conjecture is true. It follows by a previous proposition. Right? If I would have labeled them and I thought about it ahead of time, I would have said proposition A. Right? So maybe I would write like a little proof here and say like, proof. The contrapositive of this statement is precisely proposition A, QED. Right? And that would be clear. You reference proposition A, we're building more theory. Okay. So this is kind of a bad example because we didn't actually have to do anything. We already did the work. But so I'll write that out. So this is proposition. I'll call this proposition C. And again, proposition A was n even implies n squared is even, and proposition B is n is odd implies n squared is odd, right? So if I labeled them, which you definitely should do, with a contrapositive of this statement is exactly capital P proposition A. And that's it, QED. Now, there's something kind of important to understand about what this means for us. We know that, so what do we know? N odd implies n squared is odd, right? We proved that as that's proposition B, right? But then that's always true. And n squared odd implies n is odd is true, right? These two things, this compound proposition is true for all n, right? Notice the conjunction, right? So this is a special form. Recall from our earlier logic equivalencies that if P then Q and Q then P is logically equivalent to P if and only if Q. That was one of the equivalences that I might have mentioned. And it's definitely in the book, the textbook. So both of those things are true. That's always true. That biconditional statement is always true. So what we've really discovered is maybe I'll even call this a theorem. So what is the theorem? Well, the theorem states that n is an odd integer if and only if n squared is an odd integer. Right, the biconditional P if and only if Q, that's the wording for it, right? If and only if. This in mathematics is the strongest type of statement that you can have. Remember when we were going over these logic operators, I mentioned that the biconditional is almost like equivalence. In fact, that's how we defined equivalences between compound propositions, right? That's essentially what this is saying now in the realm of mathematics. N is odd is equivalent to n squared is odd because of the biconditional nature of it. We proved that, and we also proved that together, we get the strongest type of relation between these things. Which means that, it's an equivalence. We know if n squared is odd, n is odd. If n is odd, n squared is odd. We know that if one of those two things happen, we know immediately about the other. Okay. So we also know something about being even too. Right? Like what if I changed up this conjecture over here a little bit? And I said something like, so like a conjecture. Now I'll just write it as a proposition because it should be clear that it's true. And this states that if n squared is even, then n is even. Right? I didn't write conjecture this time. This is true. But why? Well, if I would have, I wish I would have labeled my propositions earlier. I'll call this proposition D. Okay. So, what's the contrapositive of that statement?
If n is odd, then n squared.
Exactly. That was proposition B that we proved, right? So when we just write that out, like the contrapositive of the statement. And by the way, in your notes, please label those things correctly so that when you're referencing back, you can like know. So proposition A was n even implies n squared is even. Proposition B was n odd implies n squared is odd. Contrapositive of the statement is exactly proposition B, which we already proved to be true. So then, because of that, we have another theorem. N is even if and only if n is squared. I mean, n squared is even, sorry. And I'm calling them theorems because technically it would have taken some work to prove them. We had to prove two things, right? To get that statement and the one I just mentioned. Which means that when you encounter biconditional statements in front of you, you have two things to prove. You have to prove that implies that, and that implies that. So you have two proofs to do when you consider a biconditional statement. Okay. And let's see if I can maybe give an example of where we actually have to use the contrapositive in a meaningful way, because we haven't actually done a contrapositive proof yet, and we should. So get out my Rosen book. So let's see. Here's a good one. So this is a proposition. It's listed as such in Rosen, so I'm going to write it that way. But more likely than not, when you encounter things to prove on your first exam, I will state them as conjectures, and you have to think about it. Okay. So what is this example? Okay. 3, 2. So if so I'm going to use this notation now for brevity. So if n is an integer, or no, I'll say let n be an integer. And then here's my statement. If 3n plus 2 is odd, then n is odd. Okay. Now, if you tried to write out scratch work for this, you would run into that same problem we encountered earlier, right? You would assume that 3n plus 2 is odd, then you would say 3n plus 2 is equal to 2k plus 1, you would try to manipulate it and you'd end up dividing by that 3. And then you have no idea if you end up with a whole number, an integer, right? So you would encounter this problem whenever, and that should be like a signal to you. If you try direct proof and you you apply an operation where you have no clue if the operation results in an integer, then you should probably switch it up, try proof by contrapositive.
That's already before.
Hmm?
That's already before.
It's false?
Yeah.
For what? Give me a counterexample.
Like,
You have to find a case where it's false. So like, if this is, remember, this is the condition, like you have to assume that 3n plus 2 is odd, and then give me a case where that's odd, but n is even. That would be a counterexample. Now, for the sake of time, I'm going to kind of rush through this one. Okay. So, scratch work. Notice now in my scratch work, I'm going to say contrapositive. Or another way of saying that is contraposition. I know contrapositive. Just for the scratch work. So now I'm not doing a direct proof, I'm doing a proof by contrapositive. So then what is, maybe in my contrapositive, I should say what? Like, what is the statement? It is what? N even implies 3n plus 2 even. Right? That's the contrapositive of that statement. And you negate the conclusion, and that implies the negation of the hypothesis. Okay? So now we're going to prove the contrapositive in the method that we know how to. We assume that and then show that it implies that. So then I'm going to assume n is even, which means that n is equal to 2k, right, for some integer k. So declare, definition, some algebra. So then what do I want to show? I want to show that 3n plus 2 is even. So I'm going to look at 3n plus 2. And I know the form of n, so this is going to be 3 times 2k plus 2. That doesn't look even, but we can make it look even by doing what? Factor out that 2. Two times an integer. See that? 3 times 2, there's a factor 2 there, factor 2 there, I take it out. So what I'm left with, 2 times that. Okay, so now for the formal proof in the last 3 minutes or so. Now, because we are not doing a direct proof, we are using an indirect method, contrapositive in this way. So I'm going to let the reader know immediately so they don't get confused. So I'm going to write by way of, say, contraposition. It's another way of saying contrapositive, it's just kind of a more elegant way, I think. So by way of contraposition, suppose n is even. Another way that you could write that is maybe suppose that n is an even integer. You all write that to be clear. So immediately, you've let them know it's contrapositive, and then you make a declarative statement. You assume something about n in this case, which if the reader knows what contrapositive is, they know to look at the statement and negate that. That's what you've assumed. Everything's good to go. Next up, definition, right? It's just like the proofs we did before. We just had to prove a different statement. That's it. So by definition, N is equal to 2 times K for some K that's an element of the integers. Using that notation because it was used in the statement of the proposition, I'm staying consistent. Okay. So then we can do some algebra. Then, comma, what is the thing? 3n plus 2 is equal to 3 times 2 times k, all plus 2. Factor out the 2. And we get 2 times 3k plus 1. Now we have to remind the reader of the definition, and we're done. Since 3k plus 1 is an integer, 3n plus 2 is even by definition. QED. QED because that proves the contrapositive, which has the same truth value as the original statement. Okay, so that's it. I'm going to stop the recording now.